Oh, okay. So nice to see you all. I actually thought there would be fewer of you at this time. So thanks for staying. I thought the last session looked and sounded fantastic. So, and I want to say that when I teach medical students about research ethics and clinical research, I always end up with a 10-minute talk they give. And I always tell them it's much harder than a 30-minute talk. Well, seems to be true, and we've now used up 1 minute. But I am going to forego some of the intro. You very nicely gave some of it. I'm director of the Center for Genomics and Society, which by itself combines technology and ethics, and the Ethical, Legal, and Social Implications program of the National Human Genome Research Institute has been my primary funder for many, many years. What I want to do today is, oh, this is so awesome, you've got my notes up. That's, thank you. Okay, so while I've been director of this center for the past 13, 14 years, a revolution in genomics has taken place. And I've been fortunate to be part of some of the research studies about the clinical application of sequencing. And what I want to do is talk about what's happened in our center and with the work that has gone on by fantastic researchers here at UNC, and then what kind of ethical dilemmas have been raised, and importantly, we're going to look at the return of research results. Now, you can see on the right-hand side the way genetics used to be thought about, literally one gene at a time, focusing on Mendelian disorders or monogenic conditions, that one gene or one alteration or variant in one gene could be identified as causal. That's where genetics was before the human genome was sequenced in 2003. It cost about $1 million to sequence the first one. How much do you think it costs today to sequence a person's genome?
$800,000.
Oh, you got it. Okay, you already know. So, right, it's massively reduced. Next generation sequencing, whether you're just looking at the exome, which is over 20,000, mostly protein coding genes, or many, many hundreds of thousands more for the whole genome. You're looking then perhaps at multifactorial conditions. You're looking at a massive amount of data. Now, when people do sequencing in a research and now increasingly clinical context, they're looking at certain sections. The literature points to certain sections in the genome that may be related to particular diseases. So you don't look at all 20,000 to try and see if a person's heart problem or cancer or neurologic disorder is related to genetics. You look at certain segments, but that is a very rapidly evolving literature. And sequencing, of course, also produces a massive amount of data that has been referred to in many different ways. Mostly it's of unknown significance. But there are also incidental or secondary findings unrelated to diagnosis. So let's just look at this first question. You tell me, if you were found to carry a rare variant that greatly increased your chances of developing a serious condition that can be prevented or treated, would you want to know about it? How many yes? How many no? How many not sure yet? Thank you. So this is the idea of actionability. Something, and unrelated to why you got sequencing. Now, historically, the return of results is not something that has been typical in research, particularly genetic or genomic research. Wasn't a standard practice for a variety of reasons. Remember, research, not clinical care. And the reasons are somewhat simple in terms of ethics. And that is, research is to produce generalizable knowledge. Okay if you benefit. If you're a patient in an early phase cancer trial, you lost all other options, you may hope for a benefit, but that's not the goal of the research. The individual benefit is the goal of clinical care. And the boundary between research and clinical care is easily blurred particularly if you're looking at patients. So it's got to be carefully guarded. Hence, return of results in research is a fraught topic. Now, until, for genomics, 2013, the American College of Medical Genetics and Genomics, ACMG, pulled an expert group together, and they decided that if somebody's getting, and in 2013, not very many centers did this, but if somebody was getting clinical sequencing, that there were, that point, they identified 56 genes who had pathogenic variants or mutations associated with them. Those would be disease-causing variants. So let's think about hereditary breast and ovarian cancer. A lot of you have heard of BRCA 1 and 2, or Lynch syndrome, which is highly related to colorectal cancer. Those were on the list of 56. ACMG, in a very controversial statement, said laboratory reports coming out of the sequencing, regardless of the indication for which the person was sequenced, must report these. This was not a consent issue, and this was not an age issue. So it was a kid, it was an adult. This is what had to happen. And there was enormous pushback after they put out these guidelines. And at the same time, while now they're saying, well, maybe people should be able to consent to this, maybe we should think about children differently than adults. Nevertheless, this kind of opportunistic sequencing was, even though it was for clinical care, had a very strong impact on research. Now, I want to tell you about our NC Gene study. Anybody heard of it here? Jim, thank you. 2 people. Jim Evans, Jonathan Berg, Cindy Powell, Bradford Powell, not related, are terrific researchers here. NC Genes it's almost done. It's actually in the second phase, a study of should and how should clinical sequencing be used in the clinic here for somebody who had maybe a suspected genetic cause of a condition, but simple genetic testing, one gene at a time, revealed nothing. How could sequencing impact on that? Would it make produce better diagnoses, et cetera? But at the same time, the investigators here, understanding clearly what was going to come out from ACMG, said, if there's these actionable findings, we think we need to return those too. So they developed a strategy, they call it a semi-quantitative metric, which means they kind of made it up, and they decided 1 was this, 2 was this, 3 was this. And there were 5 different criteria that they thought ought to determine if something was going to be returned because it was actionable. That is, preventable, no shit. Sorry about that. Really? Okay then. I will just be talking a lot faster. So these are the categories that they looked at. How big was the threat? How likely was the disease? How efficacious would the intervention be? For gastric cancer, the intervention is take out your stomach. And this is still experts talking, not talking to patients, but they said, probably not returnable because nobody would want their stomach out. Well, ask a family in Boston who was featured in the Boston Globe who all had their stomachs out because they had hereditary gastric cancer. How burdensome was the intervention and what was the knowledge base? Okay, so sounds easy, but genetics and figuring out what actionable means is really not at all easy. Because genetics itself, it has components in it that are difficult for geneticists to interpret and have been changing a lot over the past few years. These incidental or secondary sequencing findings are by definition rare. They have to be rare because otherwise, we'd all have them and we'd all have the diseases. And they occur in a population with low prior probability, which really affects sensitivity and specificity. So variant pathogenicity, that means how much is the variant likely to cause a disease. Well, this is what they come up with. This is where we are. A whole bunch is uncertain significance. On the left-hand side is benign, then likely benign, then on the other side, likely pathogenic, and then certainly pathogenic. You can see what a tremendously small percentage of variants are actually agreed upon to be pathogenic. And would you want something that's just likely pathogenic to be returned? Or even uncertain because it's your genome and you want it on your thumb drive? And who would be responsible for that interpretation? But genetics is also not so easy, just actionable, because there is incomplete penetrance, that you might have a mutation but never get the disease. And even if you have the same mutation as someone in your family, it might not be expressed in the same way. A recent article in the New York Times, I am really just about done. A recent article in the New York Times also alerted us to something that nobody really knows about either. Gina Colada is one of my favorite science authors, journalists, and wrote, "The results of your genetic test are reassuring, but that can change." Why can it change? Because geneticists all over the country are contributing to a very innovative and recently created database called ClinVar, where they say, you know, we have evidence that this mutation is actually not pathogenic. We think the data are wrong now, so others contribute, and then the actual calling of is it pathogenic or not changes. Well, if you're a patient that's been sequenced 3 years ago, you're not going to know that. The laboratory system doesn't have a way or money to return that to you. So it's, many things about genetics are changing so fast that, we need reporters to tell us about it. There were a couple of other things I'm going to not talk about, but those are just actionable findings. A lot of controversy is about, well, wait a minute, I don't care if it's actionable or not. I want to know. What if I have Huntington's in my family? What if I have Alzheimer's in my family? I want to know that. Would you want to know those kind of things? Yes? Not as many people raised your hands. Or how about something that's not very treatable, but also not very serious? And what about findings for children? There's a lot of controversy about that. And if we had more time, I would tell you about that, but I don't. So here's the last slide. Gone over 10 minutes, right? My students would be like, we are so bad. This is the last slide. This year, the National Academy of Science, Engineering, and Medicine came out with a report about what to do about return of incidental findings, or any individual findings, whether they're actionable or not. Here's where ethics and technology change, the rubber meets the road. Well, if it's in imminent danger, you have a duty to warn, no problem there. And if you're talking about what to do with participants, well, focus on the principles that we always focus on: respect for persons, beneficence, and justice. And make sure you're doing an ethical job and transparent job of telling them what you're going to do. A lot of recent research indicates that a lot of participants do want results. A lot of results, maybe even all their results, and they'll put it on the web, right? But a lot don't. Nevertheless, the harms of giving people genetic results, especially if you give them my talk first about how difficult it is to be really sure of the meaning of this, that the harms are less than anticipated. On the other hand, there's a lot of individual results that would be inappropriate to return, most important of which is something called overdiagnosis. Who knows that? It just means you're given, like, you have a BRCA1 gene. Are you going to get breast cancer? Maybe, maybe not. You may not, in which case you've really been overdiagnosed, and that will affect your insurance as well. And as I indicated, the terrain is constantly changing. So as the ethics keeps up with this, we who are only social scientists, have to be really informed, because none of it is real sure. and a lot of it is subject to media hype. Okay, thank you very much.